Imagine looking out your window and spotting a stranger standing silently in your backyard. They aren't knocking, they aren't calling out. They're just there. Maybe they're harmless, or maybe they're dangerous. You have no way of knowing. All you do know is this: if that stranger suddenly walks toward your front door, you won't have much time to decide what to do. That's the level of urgency and uncertainty we're dealing with right now because of an interstellar object known as 3I Atlas, or 3I Atlas. On December 3rd, 2025, a geophysicist quietly revealed something about this visitor that NASA hasn't exactly been discussing openly. And in just a few months, Earth will pass directly through the debris trail, the object released when it swept around the sun. This isn't just another pretty comet lighting up the sky. We already know from missions like OSIRIS-REx that asteroids within our own solar system carry the basic ingredients for life: amino acids, water, organic molecules, even the building blocks of DNA and RNA, all sealed inside ancient rocks. Now take that idea and scale it up. 3I Atlas appears to contain even richer concentrations of these same materials, except they didn't form around our sun. They come from an entirely different star system. And recently it erupted violently, blasting that material out into space, material that Earth is on track to fly straight through. Stay with me, because what this implies doesn't just update a chapter in an astronomy textbook. It cuts straight to the heart of one of humanity's biggest questions: where does life actually come from? And how common might it be across the universe? So let's start with what we genuinely know. 3I Atlas entered our solar system from deep interstellar space. Astronomers traced its path backward using Gaia star catalog data. They can follow its journey for at least 10 million years, and in all that time it never came close to any star. Not once. For millions of years, and potentially for billions before that, this object wandered through the cold, empty gulf between solar systems. No sunlight, no warmth, no solar flares. Nothing but darkness and time. In that environment, it slowly gathered material drifting through the interstellar medium: frozen gases, volatile ices, organic compounds, dust, and tiny fragments older than our sun itself. Meanwhile, cosmic rays bombarded it nonstop. Ultra-energetic particles that don't just damage matter, they alter and process it. Cosmic rays don't just damage matter, they break molecules apart, rebuild them, and trigger strange reactions that gradually turn simple chemistry into something far more complex. Then, on July 1st, 2025, we finally spotted it. By the time 3I Atlas was detected, it was already inside the solar system and already heating up. And that's when the bizarre behavior began. At around 2.5 astronomical units from the sun, about the distance of the asteroid belt, something happened that normal comets simply do not do. On September 7th, its brightness didn't rise slowly along the smooth, predictable curve we expect. Instead, it jumped by 2 magnitudes in an instant. Not a gradual ramp up, not a tiny flare. A sudden, permanent step upward. And it stayed that bright all the way to its closest approach to the sun on October 29th. In comet science, that is a massive red flag. A comet should brighten smoothly as sunlight sublimates surface ice. But this looked like a switch being flipped. The simplest interpretation is that 3I Atlas didn't just warm, it experienced a state change at that distance from the sun. Conditions became warm enough for liquid water to exist, at least briefly, on or below the surface. Not just ice evaporating, but actual liquid. The outer crust, built up over millions or billions of years, drifting through interstellar space, suddenly destabilized. The ices didn't sublimate gently, they exploded outward. This is what planetary scientists call cryovolcanism, cold volcanoes. Instead of molten lava, they erupt jets of water vapor, frozen gases, organic rich slush, and volatile ices shooting into space. And this wasn't a tiny flare from a single vent. 3I Atlas rotates once every 16 hours, spreading sunlight fairly evenly across its surface. That means this wasn't a localized outburst. It was global. Post-perihelion images from amateur astronomers confirm this. multiple jets spanning nearly 50,000 kilometers from the nucleus. That scale means intense, sustained activity. The entire surface seems to have ignited at once. Now the chemistry inside those jets is where things get truly strange. Spectroscopic data shows high levels of CO2 and CO lower than normal water content compared to typical comets. Strong nickel signatures. This is not the chemistry of a clean, simple ice ball. This is processed material, oxidized volatiles and metal-rich surfaces acting as natural catalysts. And when you mix water, iron, nickel, carbon-rich compounds, and heat, you create the perfect environment for a well-known type of reaction, Fischer-Tropsch synthesis. On Earth, we use Fischer-Tropsch reactions in industry to turn carbon monoxide and hydrogen into hydrocarbons, the basis of fuels and complex organic molecules. Now imagine that same chemistry unfolding naturally on the surface and just beneath the crust of 3I Atlas. Sunlight heats the outer layers. Liquid water briefly forms and reacts with metal-bearing minerals. And suddenly, reactions begin producing amino acids, simple sugars, and even the precursor molecules of DNA and RNA. At that point, you're not just transporting raw ingredients. You're running a chemical factory. This is where the OSIRIS-REx findings from asteroid Bennu become crucial. Bennu is a B-type asteroid inside our own solar system, not a pristine time capsule from deep space. It's been baked by the sun, hammered by impacts, and processed in ways that strip away and rearrange material. Yet when scientists analyzed samples from Bennu, they found an astonishing inventory. 14 of the 20 amino acids used in life on Earth, 33 amino acids in total glucose and ribose, the sugars that form essential biological backbones. All 5 nucleotides required to build DNA and RNA, and water locked inside minerals. In other words, even a weathered, processed asteroid like Bennu still carries a full toolbox of life's building blocks. Now compare that to 3I Atlas. Its spectral signature matches CRR carbonaceous chondrites, some of the most primitive, metal-rich, organic-laden meteorites ever found. They're rarer than Bennu's class and far more untouched, more chemically pristine, and more concentrated in the exact materials that favor prebiotic chemistry. So if a tired, processed object like Bennu contains all the essentials for life, what must something as ancient, unaltered, and interstellar as 3I Atlas hold? Almost certainly, higher concentrations of organics, more complex molecules, and likely entire families of compounds we've never seen before, formed under conditions shaped by another star system, with different radiation patterns, different elemental ratios, in a completely different early environment. And 3I Atlas didn't quietly keep these materials sealed inside. It erupted globally, blasting them into space. There's another piece that makes this even more compelling: magnetite. When iron and nickel-rich minerals corrode in the presence of liquid water, they can form Fe3O4. Magnetite, the most magnetic naturally occurring mineral on Earth. This isn't speculation or science fiction, it's basic geochemistry. We see magnetite in carbonaceous meteorites that underwent aqueous alteration, meaning their parent rocks interacted with liquid water long enough for the chemistry to alter their structure. Now apply that same process to an interstellar visitor that recently erupted across its entire surface. The implications are enormous. 3I Atlas has all the right ingredients: high nickel content, high iron content, water, and heat. Everything needed to produce magnetite. And once magnetite forms, it doesn't just sit inertly, it creates localized magnetic fields. On Earth, magnetite-rich regions create measurable magnetic anomalies. On Mars, patches of crustal magnetism are relics of ancient water activity. So for 3I Atlas, producing magnetite implies something extraordinary. It could be generating its own intrinsic magnetic field, not just a momentary plasma tail shaped by the solar wind, but a physical magnetic environment tied to its crust and near-surface layers. Why does that matter? Because magnetic fields act as shields. They deflect charged particles and reduce the damage cosmic rays cause to complex molecules. Life on Earth survives partly because our magnetic field and atmosphere protect the surface from high-energy radiation that would otherwise tear DNA apart and destroy delicate chemistry. So if 3I Atlas is generating even a weak magnetic field, just tens to hundreds of nanotesla, that could create pockets where organic molecules are partially sheltered, where complex chemistry can survive longer and evolve further instead of being wiped out. Put all of this together, and 3I Atlas stops looking like a dirty ice ball and starts looking like a traveling, long-lived chemical reactor. An ancient object drifting through space, loaded with organics, periodically heated and reawakened whenever it passes near a star, using natural geochemistry and sunlight to transform simple compounds into more complex ones. Not life itself, but everything needed to make life easier to start wherever that material eventually lands. And this brings the story right back to us. On December 19th, 3I Atlas makes its closest approach to Earth, about 1.8 astronomical units. That's not apocalyptic, but it's closer than it has been since we discovered it. By then, the main tail will be shifting, and its brightness will be fading after perihelion. Yet that strange sunward-facing jet, the anti-tail that shouldn't exist, is still active, still ejecting material, still feeding the debris stream that surrounds the comet's orbit. Fast forward to March-April 2026. Earth's orbit carries us directly through the region of space where 3I Atlas was during its most violent outbursts, near perihelion, when those 50,000-kilometer jets blasted out the most material. Solar radiation pressure and orbital dynamics will spread that material out, but not so much that it disappears. Some of it, especially the finer dust and small particles, can intersect Earth's atmosphere. So what would actually fall into our skies? If the Bennu comparison holds, and if 3I Atlas is as organic-rich as its spectrum suggests, then Earth could receive a thin rain of amino acids, nucleotides, complex carbon molecules, water-bearing minerals, metal-rich dust, all originating from another star system. Not random space debris, but chemically active material processed over millions of years and then violently reactivated in a global cryovolcanic eruption. This is where science and philosophy meet. The idea that life's building blocks, or even dormant life itself, could travel between worlds is known as panspermia. This isn't just a fringe thought experiment anymore. We already know organic molecules can survive in space. We know they can survive atmospheric entry. We've literally found them inside meteorites that crashed onto Earth. So the real questions become, how much of this material gets transferred between worlds? How often does it happen? How many interstellar objects have passed by our planet, sprinkling chemistry into young atmospheres? And how many times has Earth been dusted with alien organic material? We don't have the answers yet. But 3I Atlas gives us a rare chance to watch this process as it happens, instead of trying to reconstruct it from billion-year-old rocks. Previous interstellar visitors, Oumuamua and Borisov, hinted at possibilities, but nothing like this. Oumuamua was strange but faint, offering barely any usable data. Borisov was more like a typical comet, but small and short-lived in our telescopes. 3I Atlas is different. It's large, extremely active, chemically rich, and we're getting high-quality spectroscopy, continuous imaging, precise light curves, structural data, and all of this perfect timing lands right after OSIRIS-REx proved that even ordinary solar system asteroids like Bennu can carry enormous amounts of life's ingredients. If Bennu is the baseline, then 3I Atlas might be the extreme end of that spectrum. Here's the frustrating part. NASA's public communication is cautious, conservative. Press briefings emphasize nice photos, mention unusual activity, and file it under comet behavior. Interesting, but comfortably ordinary. Almost no one in official channels is openly talking about what Bennu's discoveries mean for an interstellar object like this. Almost no emphasis on the fact that something rich in organics from another star system has just exploded material across our neighborhood, and Earth is on track to fly through its remains. The panspermia angle, the idea that planetary systems might trade chemistry this way, barely comes up at all. Meanwhile, independent researchers, planetary scientists, astrochemists, and an increasingly sophisticated network of amateurs are putting the pieces together anyway. They're looking at the cryovolcanism evidence, The magnetite-forming chemistry, the Bennu, results the spectral classification, the timing of Earth's orbit, and they're seeing something far more important than just another comet. They see a once-in-a-generation opportunity to test whether interstellar objects truly act as couriers for the raw materials of life. So here's the real picture, stripped of PR gloss. 3I Atlas is likely an ancient object, possibly 3 to 11 billion years old, drifting between stars for at least 10 million years. 3I Atlas is likely an ancient object, possibly 3 to 11 billion years old, drifting between stars for at least 10 million years without passing close to any of them. During that long journey, it accumulated and processed a crust of volatile ices and organic compounds from the interstellar medium. Then, when it entered our solar system and reached about 2.5 astronomical units from the sun, it hit a critical threshold. Liquid water became possible, the crust destabilized, and a global cryovolcanic event erupted. Not a tiny flare, a full-surface activation. Massive jets of water, carbon-rich material, and metal-bearing particles blasted into space. Its composition matches some of the most primitive, organic-rich meteorites ever studied. It has all the right, it's no longer a fringe thought experiment. We already know organic molecules can survive deep space. We know they can survive atmospheric entry. We found them locked inside meteorites that landed on Earth. The real mystery isn't whether life's ingredients can travel between worlds. It's how often that transfer happens, and how much material actually makes the journey. How many interstellar objects have passed through young planetary systems, dropping complex chemistry into budding atmospheres? How many times has Earth been dusted with extraterrestrial organics? We don't have those answers yet, but 3I/Atlas gives us a rare chance to watch the process as it happens, instead of trying to reconstruct it from ancient rocks. Earlier interstellar visitors, Oumuamua and Borisov, gave us clues but not clarity. Oumuamua was strange but faint. Borisov behaved more like a comet, yet it was small, short-lived, and hard to study in detail. 3I Atlas is different. It's larger, it's active, it's chemically rich, and we're gathering high-quality spectra, continuous imaging, light curves, and structural data. And the timing couldn't be better. OSIRIS-REx just proved that even ordinary asteroids like Bennu can carry an abundance of organic material. If Bennu is the baseline, 3I Atlas may be the extreme case. Here's the frustrating part. NASA's public messaging that is cautious. Yes, Press briefings show beautiful images, make polite comments about unusual activity, then comfortably categorize the object as just a comet. What you don't hear is how the Bennu discoveries reshape our expectations for an interstellar visitor like this. You don't hear much about the astrochemistry angle or the fact that a volatile-rich body from another star system has just exploded material across our neighborhood, and Earth is about to pass straight through its debris. Independent scientists, astrochemists, and an increasingly coordinated amateur network aren't ignoring these connections. They're examining the cryovolcanic signatures, the magnetite-forming chemistry, the Bennu results, the spectral data, and the timing of Earth's orbit, and they're seeing something far bigger than an interesting comet. They're seeing a once-per-generation opportunity to test whether interstellar objects actually transport prebiotic chemistry between planetary systems. So here's the clear picture. Without the press-safe language, 3I Atlas is likely ancient, potentially 3 to 11 billion years old, wandering between stars for at least 10 million years without a close stellar encounter. Along the way, it collected and transformed a crust of ices and organics from the interstellar medium. When it reached roughly 2.5 astronomical units from the sun, it crossed a thermal threshold. Liquid water became possible beneath the surface. The crust destabilized. A global cryovolcanic outburst followed, not a minor flare, but a full-surface activation. Jets of water, carbon-bearing compounds, and metal-rich particles erupted into space. Its chemistry matches some of the most primitive, organic-rich meteorites we've ever studied. It has all the necessary ingredients to form magnetite and possibly generate a weak magnetic field, enough to protect delicate molecules inside. And in early 2026, Earth will drift quietly through the region where much of that material now floats. We won't send a spacecraft to collect samples. There's no time. But we don't need to. Earth's atmosphere will do the sampling for us. Microscopic grains will fall. Meteor networks will detect faint entries. High-altitude collectors and future micrometeorite studies may reveal whether those particles carry Bennu-like organics, or something even more exotic. Will this material change life on Earth in any dramatic way? Almost certainly not. This isn't a threat or a catalyst for sudden evolution, but scientifically it's enormous. If we detect interstellar dust from 3I Atlas carrying prebiotic chemistry, it's evidence that planetary systems don't evolve in isolation. They trade materials. They share ingredients. They pass chemistry across the galaxy. And that would mean the odds of life emerging somewhere else rise dramatically. Most people will never hear the deeper story from official briefings. They'll see safe headlines and polished photographs. That's why you're here, because you're willing to look past the surface and ask the questions that don't fit into a sanitized press release. So here's where we stand. A chemically rich interstellar object entered our solar system. It warmed. It may have briefly hosted liquid water. It erupted. It built complex organics. It may have generated magnetic shielding. Then it hurled that material into space, and Earth is about to fly through it. We don't yet know exactly what's in that dust. We don't know how complex the chemistry is. We don't know whether it holds molecules we've never seen before. But we're about to find out. If you want the real story as it unfolds, not just the official photos, but the analysis, the anomalies, the astrobiology implications, make sure you're subscribed. The closest approach comes December 19th. The debris field crossing happens in March and April. The data is coming whether we're prepared or not. Stay curious. Keep asking questions. And remember this, the universe doesn't evolve in isolation, and neither do we.